This is an example problem from the book which tests your skills at drawing free body diagrams and also your understanding of all the forces that can be acting under scenarios of complicated loading and variable cross sections. Shown here is a pretty useless crank where there is a handle where we apply a load F. In the book, they're applying 300 pounds vertically downward. So F would be written as a vector minus 300J in units of pounds. If we have a coordinate system whose origin is at the built-in end A, where the shaft is built into a wall, the X coordinates coming out of that wall, and then we have Y and Z coordinates as shown. So we got to figure out all the stresses that are acting in this thing. And you'll notice that if we move the force F from its current location back an amount 1.5 inches, and we put the force there, we also have to include a torque. And the torque that would be recorded right here is trying to rotate this thing in the minus Z direction. So the torque at C would be equal to 300 pounds times 1.5 inches, and it would be in the negative K direction. So we still have the force at C, which is minus 300J, and we would have a torque also. Now, if we were to remove component BC, that is this funky looking rectangular cross-section link, if we were to remove that from its support shaft at B, in order to keep it in equilibrium, we know we would need a counter torque back here that would be equal to the negative of TC, because we have to counter it. We would also need F back to this point B, and that gives us also a torque in this direction that has to be opposed by the shaft. And so we're trying to rotate the shaft clockwise when you're looking down the x-axis. So we would need a counter torque in this direction to offset it, and the magnitude of that torque would just be what? F times 4 inches, and it would be in the positive I direction. So there's a torque there that's acting on the shaft, or it's the same thing as a moment that would be acting on the component BC in order to keep it in equilibrium. So we got a lot of things going on there, and we would have to sort out the stresses brought about by all of those things. So if we were to look at the component BC, you will note that it is of rectangular cross section, a height of 1.25 inches, and a thickness of 0.25 inches, and it is exposed to a torque, which I said was 300 times 1.5 inch-pounds. And so we will have a maximum torsional shear at the midpoint of the long side. We'd be able to calculate what that tau max was from the known dimensions of the sample and the known torque that we are applying to it. So we could find that tau max in there. We also know that we would have a bending stress in this shaft that would be at the top side, and that max bending stress would be given by an my over I term, all of which is easy to calculate for this particular beam. So that's not all that difficult. And then we could go back to position A and figure out what is required to keep the shaft in equilibrium under the influence of this load F, this torque TC, and this other torque right here. And so we have a complicated stress state, and once we sort out all of those stresses from bending and torsion, we could then easily find the maximum shear stresses.